Good morning, everyone. My name is Sidi Noor Aisha Binti Muhammad Noor, and today, I am going to present our project on enhancing electric power system stability through the implementation of energy storage systems, ESS, in electric vehicles charging infrastructure. This work is a collaborative effort with my group members, Nur Badslan Nazreen Roslan, Nur Najira Noor Zaimi, Muhammad Abdul Talib Mat Yuso, Muhammad Iqbal Zakaria, Nick Hakimi Nick Ali. We will start with an introduction, followed by the problem statement and objectives. Then, I will discuss the methodology we used, present the results and discussion, and finally, conclude with the key takeaways from our project. As part of Malaysia's goal to reduce CO2 emissions by 40% from 2005 levels by 2020, the adoption of electric vehicles, EVs, plays a crucial role. However, increased EV uptake presents challenges for our power grid, particularly when it comes to fast charging stations. These stations put high demand on transformers and power lines, leading to issues such as power losses, peak demand problems, and voltage violations, which in turn affect power system stability and the longevity of infrastructure. Our project investigates the impact of EV charging station behavior on the distribution network. Specifically, we are looking at how the integration of EV charging stations causes voltage fluctuations, equipment overloading, accelerated aging, and harmonic distortion, which strain the power grid. Our objective is to identify the optimal location for energy storage systems, ESS, using the evolutionary programming, EP, technique to mitigate these issues and improve power system stability. To address these challenges, we developed a test system on a distribution network using Octave programming. We then applied evolutionary programming to improve the EV charging profile, aiming to minimize power losses and ensure the minimum voltage requirements are met. We tested the system at 3 levels of EV penetration, 30%, 60%, and 100%. Here we have a simple representation of the low-voltage distribution network we used in our study, showing the number of consumers connected to each feeder. This slide shows the load profile under different scenarios of EV penetration. As you can see, the integration of ESS helps in reducing the peaks, particularly in the early morning and late evening, leading to a more stable voltage profile. To address the challenges identified, we implemented several mitigation measures. For 30% penetration, ESS charging and discharging ensure more stable power demand, especially reducing peaks in early morning and late evening. For 60% penetration, ESS installation reduces peak demand around 8 p.m. and smooths out fluctuations, resulting in a more stable voltage profile, lower losses, and improved efficiency. For 100% penetration, before ESS installation, power demand shows more fluctuation and lower values. Regarding power losses, ESS experiences some internal resistance and conversion inefficiencies during charging and discharging, which contribute to power losses. However, by strategically placing ESS closer to load centers, we can reduce transmission losses, as shown in the table here. In terms of minimum voltage, the ESS installation significantly improves the voltage levels, particularly at lower penetration levels. For instance, the minimum voltage improved from 2.9525 to 23.959 after installing ESS at 30% penetration. This shows the effectiveness of ESS in stabilizing voltage, particularly in systems with high EV penetration. In conclusion, our project successfully optimized EV charging infrastructure to enhance electric power system stability using ESS and evolutionary programming. Integrating ESS into the grid helps smooth out demand curves, reduce peaks, and improve overall power system stability. These findings suggest that ESS can play a vital role in supporting the growing adoption of EVs while maintaining grid reliability and efficiency. Thank you for your attention.